This is the second video from Chapter 4. The first video went over basic stoichiometry, and this video concentrates on calculations to do a stoichiometry in solution. So first of all, let's go over what a solution is. You may or may not remember from the first unit when we talked about classification of matter. We said that a homogeneous mixture, another name for it is solution. So that's vocabulary I just want to remind you of. And the components that make up a solution are the solute, and that's the stuff that's getting dissolved. If there's any question about what the solute is, it is the amount that's present in the smaller amount. The solvent is the other component of a solution. It is usually what's doing the dissolving. If it's an aqueous solution, water would be the solvent. If there's any question about what the solvent is or solute is, look at the quantities of each. The one that's present in larger amount is a solvent. So if I were to tell you that air is a solution, which it is, it's a homogeneous mixture of several gases, and I asked you what is the solvent and what are the solutes in air, it's not entirely clear what's doing the dissolving and what's getting dissolved. So this is an example of what you would have to look at quantity. And it turns out that the quantity of gas that's most prevalent in air is nitrogen. So nitrogen would be the solvent. And all of the other components, oxygen, carbon dioxide, and trace amounts of several others, would be the solutes. All right, it's important for you to understand the theory of dissolving, and it's very likely on your next exam I will actually ask you to draw a model showing this, so make sure that's something you can do also. The dissolving process for an ionic compound involves dissociation of the ions from one another. So if you've got sodium chloride, for example, which is what this model figure shows, the anions represent the chlorine and the cations represent the sodium ions. And in the solid state, the ions are very strongly attracted to each other. When you put sodium chloride into water, the ions dissociate from one another, and as they do so, they become solvated by water molecules. So these red and white balls represent water molecules. Okay, oxygen in the middle, and the little white spheres represent hydrogen atoms. And so the ions become encapsulated or surrounded by water molecules, and that is called solvation. Here's kind of a close-up of what solvation looks like. So take a really good look at this, because this is probably what I would ask you to recreate on a test. So notice the cation and the anion are both surrounded by water molecules, but there's something different about how they're surrounded. Can you see what the key difference is? Let me point out while you're looking that these little dealies that look like somebody started to draw a figure 8 and didn't finish it represent partial charges. Okay, so hopefully you realize that water is a covalent molecule, so it doesn't have full charges, but because oxygen is a lot more of a hog for electrons, it ends up hogging more than its fair share of electrons, and so it gets a partial negative charge. And it gets an extra share of electrons from the hydrogen atoms it's bonded to, so they become somewhat electron deficient and have this partial positive charge. So I'm not sure if you saw the difference, but for the anion, in this case chloride, the hydrogen atoms of the water molecules are facing the chloride. Okay? For the sodium cation, it's the oxygen atoms that are facing it or surrounding the cation. That's because opposite charges attract. So in the case of an anion, which has a negative charge, it's attracted to the partial positive charges of the hydrogen atoms, and the cation with its positive charge is attracted to the partial negative charge of the oxygen atoms. All right, so in words, that's a diagram. In words, what's happening is before you dissolve the ionic compound, there exists pretty strong solute-solute interactions. So one sodium chloride unit and another sodium chloride unit are pretty strongly attracted to each other because of the opposite charges. So there are strong solute-solute interactions. Water molecules, again, before anything is dumped into them, are also quite attracted to each other. The hydrogen of one, which has a partial positive charge, is pretty strongly attracted to the oxygen of another molecule, which has a partial negative charge. So the bottom line is, in order for something to dissolve in water, the already existing attractions between solute molecules and solvent molecules must be broken. And in order for that to be a favorable process, the new interactions between solvent and solute have to be stronger than the original attractions between solute and solvent and solvent. So if that was a lot of words and you didn't follow it, you should probably jot this down and look at it later and make sure you understand it. All right, so when an ionic compound dissolves in water, it no longer stays intact as a unit as they are in a solid compound. When an ionic compound dissolves in water, it dissociates, okay, or separates into the cation and anion. So you need to be able to show this dissociation of ionic compounds. The aqueous, remember, means it dissolves in water. And make sure you keep track of how many of each ion you have. So the subscripts, when you dissociate, become coefficients. So there are 2 sodium cations and 1 sulfur anion. You also need to know the charges of these individual ions. So you have to have the common charges of the periodic table committed to memory. So let's look at another one. Let's look at one that has a polyatomic ion. So if sodium sulfate dissolves in water, it separates into the cation, which is sodium. Note that there are 2 sodium. And now the polyatomic does not separate into individual atoms, okay? The polyatomic, while it's an ion itself, the polyatomic atoms that make up this ion are covalently bonded, so they don't break apart. So if you see a polyatomic, make sure you keep it intact as a polyatomic when you're showing dissociation. The other thing that dissociates when it dissolves in water are strong acids and bases. So strong bases are just ionic compounds, so there's nothing different. But acids, of course, don't have a metal. But they have, what dissociates in acids are the hydrogen ions, okay? So here's sulfuric acid, for example. When it ionizes or dissociates in water, you get 2 hydrogen ions, and what's left over in this case is a sulfate polyatomic. So go ahead and put the video on pause and see if you can write out the dissociation of this compound. Also challenge yourself, make sure that you could name this compound. This next test will be quite challenging because you have to remember what you've already learned, which is naming and writing formulas in addition to all this new stuff. So turn off the video and then I will show you the correct answer. All right, so here we go. Magnesium phosphate is the name. And so when that dissolves in water, and usually chemists show that when something's dissolving over the arrow, and it dissociates into the individual ions. So we have 3 magnesium ions, okay, and we have 2 phosphate polyatomics. So you should be able to figure out the charges of these from the last unit. In an emergency, if you're short for time, you can do the anti-crisscross, which again works 80 to 90% of the time. But here is the dissociation of magnesium phosphate in water. All right, we're still kind of talking about definitions. We haven't gotten to our calculations yet. Electrolyte. What is an electrolyte? It's simply something that conducts electricity. Okay, you can have all sorts of fancy definitions, but the bottom line, electrolyte means something that conducts electricity. In order to conduct electricity, there must be ions present. Okay, and the ions must be free to move. So a solid ionic compound will not conduct electricity. If you tried to run electricity through granular salt, it would not travel. As soon as you dissolve that salt in water, however, the saltwater solution would conduct electricity. So the solution must either, or the ions must either be in liquid phase or must be like melted or dissolved in water so that the ions can move. Similarly, a non-electrolyte is something that does not conduct electricity, which means there are no ions. Okay? So pure water, believe it or not, does not conduct electricity. That doesn't mean you should go stand in water when there's lightning, because the bottom line is water dissolves so many things that we essentially never have pure water. There's always stuff dissolved in it. There is always some level of ions in water, and so that's why it always seems to conduct electricity. Now, remember that a covalently bonded compound, something without any metals, does not have any ions. So if you dissolve a covalently bonded molecule, for example, sugar, I think that's C12H22O or H23O12. I shouldn't have started, I don't remember. But anyway, sugar, it's all covalently bonded. And so if you dissolve it in water, the sugar water will not conduct electricity because there are no ions. All right, so the bottom line for my visual learners, a strong electrolyte is something that simply conducts electricity strongly. So the more ions you have present, the stronger it's going to conduct electricity. So what are some strong electrolytes? Strong acids, strong bases, or water-soluble salts? What are some weak electrolytes? That would mean something that conducts electricity but doesn't have as many ions present. That would be weak acids or weak bases. And then you have non-electrolytes, things that don't conduct at all. All right, so what do I mean when I say strong acids, strong bases, weak bases? Well, this is something you have to memorize. Okay, so jot that down, commit it to memory before the next test. There are 7 strong acids and 8 strong bases. And so when you memorize the strong acids and bases, you don't have to memorize any weak ones because all of the rest of them are weak. Okay? So you notice some trends that might help you remember these. All of the halides, chlorine, bromine, iodine, they all are strong acids except, do you notice what halide isn't there? Hydrogen fluoride. That is not a strong acid. So it's the only one of the halides. And then notice how your chlorate and perchlorate are both strong acids. And then the kind of side ones are nitric acid and sulfuric acid. Okay. The trend for strong bases, all of these metals in this first row are from group 1A. Okay. So if a base, and it's a base because it has, well, the OH makes it a base in this case. All of these bases that have a group 1A metal are strong bases. And then some of the group 2A metal hydroxides are also strong, but it's the heavy ones. If you look on a periodic table, calcium, strontium, and barium are toward the bottom of row 2A. All right, so those are strong acids and bases. What do we mean? A strong acid, and I'm going to abbreviate acid, just call it HA, okay? A strong acid in water will dissociate 100% into ions, okay? That means for every single molecule of HA you have dissolved in water will 100% dissociate. None of the original intact HA will be left in the water. Same thing with a strong base. So let's call our strong base, we'll use sodium hydroxide for an example. That's a strong base. If you put sodium hydroxide in water, you get 100% of the ionized form. Okay, none of the intact sodium hydroxide is left. So look what you've done here. By completely dissociating it, your concentration of ions has gone way up. That's what makes them strong acids, strong bases, and strong electrolytes. Here is another memorization. So it's probably time to either print these two slides out or make a note card and just kind of start carrying it around with you. So these are solubility rules for ionic compounds. Okay, most ionic compounds are soluble in water, but not all of them. But there are some trends, okay, that make it soluble. All of these, well, the first three, are metals from group 1A, lithium, sodium, potassium. So if an ionic compound has an element from group 1A, it is soluble, okay, no matter what the anion is. If the cation is from group 1A or ammonium, the ionic compound is soluble. There are some other groups that are virtually always soluble. Nitrates are soluble, so let's say I had something like magnesium nitrate, okay? And I said, is this soluble? You would hopefully remember, oh, it's got a nitrate in it. It's soluble, yes. Okay, this polyatomic is called acetate. That is also virtually always soluble. So let's look at calcium acetate. All right, so same thing. If I said, is this soluble? You would say, it has an acetate group in it. Yes, it's soluble. All right. Now, so just going through the rest of them, notice if the anion is one of the halides. That is almost always soluble. But notice there are some exceptions for the halides. First of all, notice that fluoride is not one of the always soluble ones. Okay. The exceptions are silver, mercury, and lead. What does that mean? Okay, so that means if I have something like magnesium chloride, that is soluble. Okay, it's got chloride. Chloride groups are almost always soluble. Okay, and magnesium is not one of the bummers that mess it up. But what about silver chloride? Okay, you first might say, oh yeah, I think maybe that's soluble because it has a chloride. But then you're like, is silver one of the exceptions? Yes, it is. So silver chloride is not soluble. So get familiar with how to use this table and memorize these trends or make note cards or something. There are some ionic compounds that are virtually always insoluble, okay? And hydroxides, remember now, unless they have any of the group 1 metals. So NaOH is soluble, okay? But let's think of another one. Magnesium hydroxide is not soluble, okay? It's a hydroxide and it's not saved by having a cation that's from group 1A. Sulfides are almost always insoluble. Carbonates are, and phosphates are. So calcium carbonate, for example, is that soluble? No. Okay, carbonates in general are not soluble, and calcium is not on the always soluble list. And it turns, guess what? Guess what calcium carbonate is? That is chalk. Okay, so chalk is actually an ionic compound, but it's not soluble in water. All right, so the rest of this presentation is calculations, okay? So in solution, we're not, we have some different vocabulary, and probably the most common way to talk about quantity of solution is with a value that we call molarity, which I will spend the next few slides discussing. And that's because with solutions are a type of mixtures, and so unlike a compound, the composition of a solution can change. You can have one that's very dilute, which means it doesn't have very much solute in it, or one that's very, very concentrated with a lot of solute. So just make sure you understand what dilute and concentrated mean. It has to do with how much solute is dissolved. All right, so here is the formula for molarity. First thing I want to point out is the abbreviation for molarity is a capital M. It must be capital because little m means something else. What molarity equals is moles of solute, that's what you're dissolving, over liters of the entire solution. Notice it's important, this denominator is not liters of the solvent alone, it's liters of the entire solution. So here's an example. Let's say we have a 1 molar solution of sodium chloride. What does that mean exactly? That means that there's 1 mole of sodium chloride in 1 liter total of the solution, of the saltwater solution. So what if I told you to go to the lab and prepare 1 liter of a 1 molar solution of sodium chloride? How would you go about doing this? Well, you can't, a chemist doesn't know exactly how much 1 mole is, so the first thing you need to do is get that 1 mole of sodium chloride and convert it to grams, because grams is something we can all relate to and weigh out on a balance. Then you would weigh out the 1 mole of sodium chloride, which would end up being 58.44 grams, which is just the molar mass of sodium chloride. You would put it in a special piece of equipment, this glassware, called a volumetric flask. And that has been hand blown to a high degree of precision. So this is when you want to make a very precise solution concentration. So you add the solid, the sodium chloride in this case, to the volumetric flask, and you start to add water. Now, you ultimately want to get the volume of the entire solution. That means the volume of both the sodium chloride and the water to be exactly 1 liter. So as you add water, you're going to be shaking this volumetric flask around, dissolving all the sodium, because that sodium chloride is going to take up volume, take up space. And so you want it all dissolved before you completely fill with water. Once it's dissolved, you want to add the water drop by drop by drop till the bottom of the meniscus lies right on an etched line. So a question I often ask students is, why can't I, for example, weigh out the 58.44 grams of sodium chloride and then just add 1 liter of water to it? Why can't I do that? That's because your total volume is going to be more than 1 liter, because that sodium chloride takes up space, takes up volume. All right, so here's a couple of memory tricks for people who maybe are not crazy about algebra. So again, here's molarity. So if we were to abbreviate that solution, capital M for molarity equals moles of solute over liters of solution, okay? So you're going to have to rearrange that because sometimes you're going to have to solve for liters, sometimes moles, and sometimes molarity. So the magic triangle for that is down here, and really all you have to remember if you're going to use it, that moles of the solute goes on top. Doesn't matter in which order you have molarity in liters as long as they're on the bottom. So remember how to use this triangle. Whatever you're solving for gets covered up. So let's say that I asked you to solve for volume or liters of solution. So you're going to cover up the liters, that's what you're solving for. And what's left in this triangle? What's left are moles on the top over molarity in the bottom. So if you take moles and you divide them by molarity, you're going to get liters. So there'll be a lot of that type of calculations. Here's an example. This is a straightforward one. You don't have to rearrange the equation. What is the molarity if you have 34.6 grams of sodium chloride dissolved so that you get 125 mils of total solution? Remember the formula for molarity. Commit that to memory. Okay. Now we need moles of solute. The solute is sodium chloride. And so we need to calculate moles first. We get moles by starting with grams. Okay. If you want to see it in terms of unit cancellation, it would look like this. You'd have to put grams down there, 1 mole on top, and then the molar mass of sodium chloride goes here, which happens to be 58.44. Okay, and so we end up, that is 0.592 moles of solute. Okay, now they were nice enough, they gave us the total volume of the solution, so we just plug that in. Make sure your volume has units of liters. Sometimes a problem will give you milliliters and you will need to convert it. So the concentration of this solution is 4.74, we say molar. Here's one that's a little trickier, but I would like you to try it on your own. So I suggest turning off the video, trying to work it out, and then I will go through it with you. So a hint to get you started, let's write the formula. And when you're working out free response on my test, even if you don't have time or aren't quite sure how to work through something, if you write the formula down that's appropriate, I often give a point credit for that. So start by writing on the formula that you know you need to use. And the problem will always give you 2 out of these 3 values. So let's see what they're giving us. They're giving us value, no, they're asking us to solve for volume. Okay, so solve for liters. They gave us the molarity, okay, so 0.245 molar. They gave us that. And they gave us moles, 1.75. So we can plug that in. And we're trying to solve for liters. So now you're going to rearrange that algebraically, or if you don't remember how to do that, you're going to learn how to use the magic triangle. So if we rearrange this, liters equals 1.75 divided by 0.245. The only thing left to do at this point is when you do the calculation I just set up, you would get 7.140 liter. Hopefully you read the problem carefully enough to see that they asked for milliliters. So, and that's a really common conversion, so make sure you know the conversion factor. There is 1 liter for every 1,000 milliliters. So your final answer in milliliters is 7,140. Now this is often one of my short essay questions on my exam, and it is based off a slide that we did 3 or 4 slides ago when I told you step by step how to prepare a certain molarity of solution. And I would like you to go ahead and try this. This is your practice to make sure you could answer a test question like this. Anytime you see a question that says, how do you prepare? It is 2 steps. The first step is a calculation, and the calculation should ultimately tell you how many grams of solute do you need to weigh out. So you need to get it in terms of grams for the chemist to go in the lab and weigh out. The second thing you need to do in these type of problems is describe in words how to make the solution. So what type of glassware you use and the process you have to use to make sure you end up with the correct molarity. So go ahead and try to turn the video off, and then I will go through it again with you. The first thing you need to remember is what molarity stands for. So 0.5 molar means that there are 0.5 moles of the solute, which is sodium hydroxide. So there are 0.5 moles of sodium hydroxide, okay? And so we want to figure out how many grams 0.5 moles of sodium hydroxide is. So here's that. You're going to multiply moles by molar mass, and we find that we need exactly 20 grams of sodium hydroxide weighed out. So there you're done with your calculation. So then you use words to say what to do with that. You would add the 20 grams of sodium hydroxide to a volumetric flask and add distilled water while dissolving the sodium hydroxide until the total volume of the solution reaches the 100 milliliter mark on the volumetric flask. So we've been talking about molarity of solutions. Hopefully you remembered that I told you you need to be able to take an ionic compound and show its dissociation when it dissolves in water. Okay. Now what happens, because the original ionic compound separates into cation and anions, the molarity of the ions themselves is different than the molarity of the original intact ionic compound. And the molarity of each ion depends only on its coefficient. So if you started with a 1 molar undissolved solution of iron perchlorate, you're going to end up with a 3 molar solution of perchlorate ion. Okay? That's because for every 1 iron perchlorate you started with, you got 3 perchlorate ions. So it's 3 molar in perchlorate ions concentration and 1 molar in iron ion concentration. So you need to be able to understand this mole ratio and concentration of ions. So give this a shot. This is, you need to show the dissociation for magnesium phosphate, and then tell me the molarities of the cation and anion. I would try this on your own first, turn the video off, and then I will work it out for you. So this is the same ionic compound we dissociated a few slides back. So I'm going to do it again. Our cation is magnesium. You need to remember the charges on the ions. If you don't show the charges, you will not get full credit. Yeah, that's a 2. Okay. All right, so our original concentration of the undissolved magnesium phosphate was 0.175. For every 1 magnesium phosphate that dissolved, we got 3 magnesium cations. So the concentration of the magnesium cation is 0.175 times 3. And that is, I think, 0.525 molar is the concentration of magnesium ion. And 2 times 0.175 is the concentration of phosphate ions, and that is 0.350 molar. The final thing we're going over in this video is what happens when you dilute a solution. There's a calculation that goes along with that. Why do we care? Chemists will often make up what they call a stock solution, which is a very concentrated solution, and then they just take little bits of that concentrated solution and dilute them down to use over and over. So I'm going to skip over this. All right, so the formula, whenever you have a dilution calculation, here's the formula, okay? What that's saying is the molarity of the original stock solution times the volume of the original stock solution that you used equals the molarity of the diluted solution times the volume of the diluted solution that you made. So it's molarity times volume equals molarity times volume. Here is a sample problem. So the stock solution, the concentrated, is 10 molar, and it wants to know how much of that, how many liters of that should you take to make a 0.5 molar. That's quite a bit diluted, right? Instead of 10 molar, it's 0.5 molar. And they want 3 liters of that 0.5 molar. So I would say the most common student error is to kind of mix up which M goes with which V, etc. So I usually read these problems and go through then label them. So I know that the stock solution, 10 molar, is M1 in this equation. And make sure you get the volume that goes with that M1. So V1 is what we're trying to solve for. M2 is 0.5 and V2 is 3 liters. So you plug those into the equation. So here's the last slide, and it's important if you want to retain what you were just patient enough to listen to. It's important that you try to work a couple of problems on it right now. Okay, if you turn this off and try to work problems later, research has shown that you lose most of what you learned. So turn the video off, see if you can work these out, and when you're ready, turn it back on, and on the next slide, I will have them worked out for you. Okay, so the first problem on that page asked you to prepare a diluted solution that was 0.5 molar, and they said they wanted 250 milliliters of it. They said the concentration of the original stock solution was 1.7 molar, and they wanted you to determine what volume of this stock solution you needed in order to make the diluted solution. So we're solving for V1, okay? So rearrange this equation to solve for V1, which means you divide both sides by 1.7, and you get this. Now, very important, so listen really carefully. Notice that although volume is typically liters, I kept my volume in milliliters. The really cool thing about this equation is it doesn't matter what units you use for volume as long as they are the same units on both sides, because units will end up canceling because they are on both sides. So it's a lot easier if you're given milliliters to just keep it in milliliters. But what that means is the answer you get is also going to be in milliliters. So if you plug that into your calculator, you get that the volume of the stock solution that you need is 73.5, okay, and in this case, the unit is milliliters, just as the 250 was. All right, so this is a tricky one, and I'm wondering if anybody caught on to it. Don't feel bad if you didn't, but if you did, pat yourself on the back. So our stock solution is, there's 18.5 milliliters, and the original concentration of the stock solution was 2.3 molar. You probably figured out that we're trying to solve for the concentration or molarity of the diluted solution, but what you may have fallen trapped to is what the volume of the diluted solution is. If you carefully read the wording of that problem, it says that this amount, this volume of concentrated solution was added to 250 milliliters of water. Okay? So what is the volume of the final diluted solution? It's 18.5 milliliters plus 250 milliliters. So the final volume is 268.5 milliliters. And so now you need to rearrange to solve for M2, which means you need to divide both sides by 268.5. And when we plug that into our calculator, we get that the molarity of the diluted solution is 0.158 molar. So you can kind of double check yourself. You want the molarity of the diluted solution to be less than the stock solution, and it is. So just kind of a sanity check. The third and last problem is very similar to the second problem that we just did, except again, compare the wording of those two. The last problem, the third problem, says that you start with the same 18.5 milliliters of the 2.3 molar stock solution, but it doesn't say you add to that 250. It says you add enough water until the final volume is 250. So now we're going to get a slightly different molarity for the diluted solution. So in this case, it is 0.170 molar. So pay real close attention to that wording so you don't get caught up by that. That's it for this second video.